Hello everyone, this video is about inference for two population means, specifically for comparing the population means in the case of paired samples. So today we are going to look at how to conduct hypothesis testing for the comparison of the two population means in the case of paired samples, and we'll see how to construct a confidence interval for the population mean of the differences between the paired samples. In a paired sample case, we may be interested on a single quantitative variable of interest, which is measured on two different occasions. So paired sample is particularly applicable for determining the effect of a particular treatment. So in this case, the response of interests will be recorded before applying that of the treatment of interest, and then that response variable or response of interest will be also recorded after applying the treatment of interest. So here the objective is to determine the impact of the presence and absence of a particular treatment, and this will yield a response which is called pre-post treatment. And paired sample is also applicable for the comparison of two different types of treatments, let's say treatment A and B. So here the first treatment, let's say treatment A, may be applied on the units of interest, and then the response of interest will be recorded. And next, treatment B will be applied on the same experimental units, and the response of interest will be again recorded. So paired sample is applicable either for determining the effect of a particular treatment, or it can be also used for comparing two types of treatments, let's say treatment A and B, that are applied on the same or similar experimental units. Specifically, in a paired comparison, we will have a pair of the same or like that of same individuals, or you could have a pair of identical experimental units like that of identical plots of land. So once we have this pair of the same or identical experimental units on one pair of on one member of each pair, one of the treatment will be applied, and on the other member of the pair, the other treatment will be applied. Then on each pair, the response of interest will be recorded, and the interest is to determine whether the population mean difference of this quantitative variable is different between these two members of the pair. So the response of interest is going to be recorded on each pair, and actually the analysis relies on that of the differences. So for example, if we have two types of treatments, treatment A and treatment B, and if we have n experimental units, then for experimental unit 1, x11 may be the response of interest after applying treatment A, then x21 can be that of the response of interest after applying treatment B. So here these two observations x11 and x21 are extracted from unit 1. Similarly, for unit 2, the response of interest after applying treatment A could be x12, and after applying treatment B, it could be x22. And here x12 and x22 come from that of unit 2. Similarly, for that of unit n, x1n may represent the response of interest after applying treatment A, and x2n may represent the response of interest after applying treatment B. And again here, x1n and x2n come from that of unit n. Therefore, we have n units from each unit, our response of interest is recorded 2 different times or on 2 different occasions. And in the case of evaluating the effect of the presence and absence of a particular treatment, X11 may represent the response of interest before applying the treatment of interest, and X21 may represent the response of interest after applying the treatment of interest. So the same happens for that of unit 2 and that of unit N. Then instead of the actual observed values of the response of interest, like X11 and X21, X12 and X22, X1N and X2N, the analysis relies on that of the differences of each pair of response. So we are interested, for example, for unit 1 on the difference X11 and X11 minus X21. Let it be D1. Similarly, the difference between X12 and X22, let it be D2. Similarly, the difference X1N minus X2N, it can be Dn. Therefore, our analysis relies on these differences instead of the actual observed values of each pair of information extracted from each individual. And here the objective is actually whether the population mean of the differences, population mean of these differences is actually 0 or not. So if the population mean of these differences is actually not significantly different from 0, then in that case the particular treatment has no significant impact, or in the case of two treatments, treatment A and B, we can say the two treatments are not significantly different, or both of these treatments have, let's say, the same effectiveness. But if the population mean of the differences is significantly different from 0, in that case, the effect of treatment A and treatment B is different, and similarly, for a particular type of treatment, we can say the treatment is effective. That means the treatment may have either an increasing or a decreasing effect on the response of interest. Then once we have these differences, D1, D2, Dn, we can obtain the summary statistics. The sample size here will have n, and we have n differences, and we can also calculate the of the sample mean of the differences, D1 plus D2 plus Dn divided by n. Similarly, we can calculate that of the sample variance of the differences as 1 over n times the sum of the square of the deviation of each difference from the mean difference. And similarly, we can obtain that of the sample standard deviation of the difference as the positive square root of that of the variance of the differences. Then the interest in paired samples is whether the average of the differences mu d is 0 or not. The average of the differences. These differences d1, d2, dn are calculated from the sample data, but we are interested in testing for the population mean of the differences. The population mean of the differences. So if this population mean of the differences is significantly different from 0, treatment A and treatment B have significantly different effectiveness, and in the case of a particular treatment, that treatment has a significant effect, which could be either an increasing or a decreasing effect. Then here, as usual, let's look at the steps for comparing these means in the case of paired samples, or for testing whether the average of the differences is actually 0 or not. So first we have to state the null and alternative hypothesis. So we will have either of these three options. In the first option, H naught may be mu D equals 0. That means the population mean of the differences is not significantly different from 0. And H1 could be mu D is different from 0. That is, the population mean of the differences is significantly different from 0. Therefore, here we will have that of the two-sided test. And in the second, H naught may represent the of mu D equals 0, and H1 could be mu D less than 0, which states the population mean of the differences is significantly less than 0. And similarly, for the third option, H naught may represent again mu D equals 0, and the alternative could be H1 mu D is greater than 0. That means the population mean of the differences is significantly greater than 0. Then here in option 2, this is a one-sided test, specifically left-tailed test. And in options 3, this is again a one-sided test, and this is specifically a right-tailed test. Then once we state the null and alternative hypothesis, next we have to specify that of the level of significance alpha, and we have to obtain the corresponding critical value or tabulated value based on the theoretical statistical distributions. Then if the alternative hypothesis is a different from type, like here, then the tabulated value is going to be calculated as T alpha over 2. The level of significance should be divided by 2. And for that of a one-sided test, which can be either a left-tailed test or right-tailed test, the tabulated value can be obtained as T alpha. Then the third step is to state that of the appropriate test statistic and obtain its corresponding calculated value, or the value that is going to be obtained using the sample data. Then if the population variance of the differences, or if the population standard deviation of the difference is given, then the test statistic will be based on that of a normal distribution, which can be determined as sample mean of the differences minus the population mean of the differences. This is actually 0 under the null hypothesis, and divided by the population standard deviation of the differences over that of root of the sample size. Since this will have a normal distribution with mean 0 and variance 1. But if the population variance of the differences or the population standard deviation of the differences is not known, but if we know that n is sufficiently large, specifically if n is greater than or equals to 30, again the distribution is going to be that of a standard normal distribution, and the calculated value of the test statistic is going to be determined as sample mean of the differences minus the population mean of the differences, which is actually 0 under the null hypothesis, divided by the sample standard deviation of the differences over root of the sample size. So in this case, the population standard deviation is known. We used sigma d, but here the population standard deviation sigma d is not known. Instead, the sample standard deviation of the differences is used. But if the population variance or standard deviation of the differences is not known, and if the sample size is also small, which may be less than 30, in that case the distribution to be considered is that of a t distribution, and the calculated value t calculated is going to be obtained as the sample mean of the differences minus the population mean of the differences, which is actually 0, divided by standard deviation of the differences over root of that of the sample size. Then once we obtain the calculated value of the test statistic and the tabulated value from that of the theoretical statistical distributions. Then next we need to make a decision, and the decision is based on the comparison of that of the calculated value of the statistic and the tabulated value. Then if the calculated value in absolute value is greater than or equal to that of the tabulated value, or if the p-value is actually less than the specified level of significance, H naught can be rejected. Otherwise, we do not reject H naught. And based on the decision, finally we will have a conclusion. Now let's consider a particular example for illustrating how to conduct hypothesis testing for the case of paired samples. So the example here says a medical researcher wishes to determine if a pill has an effect on reducing the blood pressure of individuals. The study involves recording the initial blood pressure of 15 women. After they took the pill for 6 months, their blood pressure are again recorded as shown in the table below. Then the question says, do the data substantiate the claim that the pill reduced blood pressure of the women? So here we have 15 women. So for woman 1, before taking the pill, the blood pressure of that individual is 70, and after taking the pill, it is 68. Then these two observed values come from a single woman. Therefore, these two observations are paired observations because they have the same source. Similarly, for the second woman, the blood pressure before taking the pill is 80, and after taking the pill is 70. Then this 80 and 70 come from the second woman. Therefore, this is again a paired sample. And the same is true for that of 3, 4 up to woman 15. So the interest is to determine whether the pill has an effect in reducing the blood pressure of women. So here, for example, 70 minus 68, it is 2. Therefore, here for woman 1, the pill has a decreasing effect. Similarly, 80 minus 72, here the difference is 8. And again, the pill has a decreasing effect. 72 minus 62, it is 10. Again, for the third woman, the pill has a decreasing effect. And if we go somewhere, let's say here, for woman 11, 74, 74, then here the pill doesn't have any effect. And here, if we consider woman 14, 68 minus 72, here the difference is minus 4. Therefore, for this woman 14, the pill has an increasing effect in the blood pressure of that woman. So, for some of the individuals, the pill may have an increasing effect, and for the other, it may have a decreasing effect. And here, particularly, we are interested in testing whether the pill has an effect in reducing the blood pressure. Therefore, here, from this question, we have to identify and we have to know that here the test is a one-sided test. So here let μd be the population mean of the differences in the blood pressure of women. The population mean of the differences. Then based on the observed values of the blood pressures in each woman, the difference for woman 1 is 2, the difference for woman 2 is 8, for the third it is 10, and so on. Therefore, for most of the women, the difference is positive. But here for these two individuals, the difference is negative. And again, for these two individuals, the difference is 0. Therefore, our interest is whether the population mean of these differences is actually 0 or not. Then once we obtain these differences, we can obtain the summary statistics. The sample size here we have 15, and here the sample mean of the differences is nothing but 1 over n times the sum of the differences, which becomes on average 8.8, which is positive. Then that means here the pill has a decreasing effect. But this decreasing effect is for the sample data. Our interest is for the population. Therefore, we are going to test whether mu d is significantly different from 0 or not. Similarly, the sample variance of the difference is SD square, which is just 1 over n minus 1 times the sum of the square of the deviation of each difference taken from the mean difference, and it becomes 120.457, and the sample standard deviation of the differences becomes 10.98. Then here to test that of the hypothesis which states that the population mean of the differences is not significantly different from 0 or is significantly different from 0. First, we have to test the null hypothesis as mu d equals 0. That means the population mean of the differences in the blood pressure of women is not significantly different from 0. Then, if this hypothesis holds true, that means the treatment has no significant effect, or the pill has no significant effect on the blood pressure of women. And the alternative, we have to state as mu d greater than 0. The question of interest here says whether the pill reduced blood pressure. Therefore, if the pill reduced blood pressure, then the difference before minus after is going to be positive. 70 minus 68, it is positive. 80 minus 72, it is positive. Therefore, in order the pill reduce the blood pressure, the second measurements or the after measurements should be smaller. Then the difference before minus after will be greater than 0. Therefore, here the alternative hypothesis is mu d is greater than 0. That means the pill has a significant decreasing effect in the blood pressure of women, or the mean of the differences in the blood pressure of women is significantly larger than 0. Then once we state the null and alternative hypothesis, next we have to state the level of significance and obtain that of the tabulated or critical value. And here the level of significance is not specified, so let's consider that of a 5% significance level. And here, since the sample size n is less than 30, specifically the sample size is 15, therefore the critical value is going to be calculated using that of the t distribution. So the tabulated value is T alpha with n minus 1 degrees of freedom. Now here we do not divide alpha by 2 because here we have a one-sided alternative hypothesis. Therefore it should be T alpha with n minus 1 degrees of freedom, and this is T 0.05 with 14 degrees of freedom. Then you can easily obtain the value from the T distribution as 1.761. Then next we can obtain that of the calculated value of the test statistic, and this calculated value of the test statistic is the sample mean of the differences minus the population mean of the difference, which is actually 0, divided by standard deviation of the differences over root of the sample size. Then the sample mean of the differences, it is 8.8. Mu d under the null hypothesis, it is actually 0. 0, and standard deviation of the differences we already obtained as 10.98 over root of 50. Then this becomes 3.10. Then for making the decision whether to reject or not to reject the null hypothesis, we need to compare this calculated value 3.10 with this tabulated value 1.761. Then here 3.10, it's positive, and this value is actually greater than this value 1.761. Therefore, the null hypothesis should be rejected. If this null hypothesis is rejected, we are in favor of the alternative hypothesis, and we can conclude that the pill has a significant decreasing effect in the blood pressure of women. Therefore, the calculated value, which should be considered in absolute value, 3.10, is greater than that of the tabulated value, which is actually 1.761. Therefore, H0 can be rejected. Or if we calculate the p-value using statistical software, it will be around 0.0039, and this p-value is less than that of the significance level, which is 5%. Therefore, again, we can decide that H0 can be rejected. Then once H0 is rejected, we are in favor of the alternative hypothesis, and we can conclude in this way. Therefore, the mean of the differences in the blood pressure of women is significantly larger than 0 at 5% level of significance. That is, in other words, the pill has a significant decreasing effect in the blood pressure of women at 5% level of significance. Now let's consider that of the construction of a confidence interval for the population mean of the differences. So the 1 minus alpha times 100% confidence interval for the population mean of the difference mu d is determined as if the population standard deviation or the population variance of the differences is known, we can construct the confidence interval as the sample mean of the differences minus z alpha over 2 times the population standard deviation of the differences over root of the sample size. This will be the lower bound for the confidence interval, and the upper bound is the sample mean of the differences plus z alpha over 2 times the population standard deviation of the differences over root of the sample size. Therefore, when you say confidence interval, it is nothing but it is the construction of an interval in either sides of the point estimate. So here we have the population mean of the differences. The point estimate for the population mean of the differences is nothing but that's of the sample mean of the differences. Then considering this as a center, we need to construct an interval by subtracting a certain value, which is called margin of error, and by adding that value, which is actually the margin of error. Therefore, when the population variance or population standard deviation of the difference is known, therefore the that's of the critical value or tabulated value for the confidence interval is based on the normal distribution, specifically based on the standard normal distribution. Therefore, here we have to have the alpha over 2. And again, if the population variance or population standard deviation of the differences is not known, but if we know that n is sufficiently large, specifically if it is greater than or equals to 30, then in that case, again, the critical value is based on the standard normal distribution. But here, since the population standard deviation of the difference is not known, we use the sample standard deviation of the differences. Therefore, the difference between this one and this one is, here we use the sample standard deviation of the differences. Here we use that of the population standard deviation of the differences. But if the population standard deviation of the differences or if the population variance of the differences is not known, and at the same time, if the sample size is small, specifically if it's less than 30, now the critical value or tabulated value for the confidence interval is based on that of a t distribution, and this critical value is t alpha over 2 times t alpha over 2 with n minus 1 degrees of freedom. T alpha over 2 with n minus 1 degrees of freedom. And the other is here, just the sample mean of the differences, sample standard deviation of the differences, and also the sample size. And the same is true here, just we change the minus to plus. Therefore, here, if the confidence interval for the population mean of the differences includes 0, then the null hypothesis of a two-sided test cannot be rejected at the specified level of significance. But if the confidence interval doesn't include 0, in that case, the null hypothesis of no difference can be rejected at that level of significance. Therefore, if this confidence interval contains the value 0, that means the population mean of the differences is not significantly different from 0. If this confidence interval contains the value 0, then we can conclude that the population mean of the differences is not significantly different from 0. But if this confidence interval doesn't include 0, then in that case we can say the population mean of the differences is significantly different from 0. Then if the population mean of the differences is significantly different from 0, that means the treatment is effective, which could be either an increasing or a decreasing effect. So let's consider again the previous example for the construction of the 95% confidence interval for the mean difference of the blood pressure of women. Therefore, in our particular example, here we have this example, and here we have calculated the sample mean of the differences as 8.8 and the sample standard deviation of the difference as 10.98. Then the 95% confidence interval for the population mean difference of blood pressure among the women is obtained as the sample mean of the differences plus or minus t alpha over 2 with n minus 1 degrees of freedom. Now the sample size is 15, which is small. Therefore, this critical value should be based on the t distribution. Then times standard deviation of the differences over root of the sample size. This is just 8.8 plus or minus 2.145 times 10.98 over root of 15. Now here note that for the construction of the confidence interval, always we use the critical value as z alpha over 2 or t alpha over 2 with n minus 1 degrees of freedom. But for hypothesis testing, we could have either a different from alternative hypothesis, less than type alternative hypothesis, or greater than type alternative hypothesis. And for the previous hypothesis testing example here, we are interested whether the pill reduced the blood pressure. Therefore, here the alternative hypothesis was one-sided. Due to this one-sided alternative hypothesis, we obtain the tabulated value as T alpha. But for the construction of the confidence interval, we are going to consider T alpha over 2 with n minus 1 degrees of freedom. Therefore, here this value T alpha over 2 with n minus 1 degrees of freedom is different from T alpha with n minus 1 degrees of freedom. T alpha with n minus 1 degrees of freedom is used in the previous hypothesis testing example, but for the construction of the confidence interval, we have to use T alpha over 2 with n minus 1 degrees of freedom. Therefore, here is the value is 2.145, which is different from that of the one that we have used for the hypothesis testing, 1.761. Therefore, the lower bound for the population mean of the differences is 2.72, and the upper bound for the population mean of the differences is 14.88. Now, this confidence interval doesn't include the value 0. Therefore, this means the pill has a significant effect on the blood pressure of women at 5% level of significance.